I'm just double checking if we're live. Yuvraj is already there on the YouTube page, so that's awesome. Great to see you, Yuvraj, like always. I believe we're live. I have this pending over looming paranoia of messing up everything so many times that I always want to double check. But I believe things are set, so I guess we can get started. Hey everybody, welcome back to the Keras reading group. We're going through, let me switch this. We're still in the middle of going through this book. It's an incredible book, and if it's the first time that you're joining, I'm fumbling because I'm too excited. If this is the first time you're joining, we're reading Deep Learning with Python, second edition by Francois Chole. It is one of the best resources on Keras, and we have been reading it for a while now. Hey Akash, great to see you as well. Hey Anush, thanks for joining us, everyone, and thanks to anyone who's watching the recording as well. So far we've been reading the book, and we're right, I believe, across the 60% marker. So this is the fourth session, and I have an, like always, ambitious agenda. If I get to cover 70% of this, I'm happy by that. Even if I cover 50% of it, I'm still happy, because my goal is to make sure whatever I cover here is high quality. So the agenda for today is, we'll not implement, we'll run through an implementation of ConvNext. We'll understand what is time series, and we'll understand what is attention. So quite the bulky agenda, like always. Last week we had understanding of ConvNets and advanced computer vision, which means what is image segmentation, which is what is object detection, all of those things. So this, I said, is the like I said, is the fourth session, and I believe we'll have two more sessions. And for the last one, I have planned to run a blogathon where I'll invite everyone to write a blog, and hopefully we can share some, distribute some prizes amongst the winners. So just as a reminder, something to keep in your head, please consider uh, submitting to 27 days of Keras, or please try to think of any ideas that you can blog about in Keras. Again, this all of this is just to encourage you all to participate in contributing to open source, or starting your or not really starting, you're far ahead of the curve, but to propagate or to propel your learning journey in deep learning. So here's the agenda for today. I'll quickly recap what we learned in the last session. We're already doing that. From there, I'll try to summarize chapter 9 through 11, and we'll go through what is ConvNext. I believe I'll first summarize chapter 9 and then jump onto ConvNext. So I'll jump around a bit, and I want to first theoretically explain what is attention. So give you a high level understanding, and we might have a guest from one of the companies that builds models related to attention or transformers. That might happen next week. I don't want to spoil anything, it's still in the works. If it doesn't, fortunately or unfortunately, I'll still cover what are attention based models or what are transformer models in Keras Code next, in the next session. So for today, it'll just be a high level overview, and like always, please keep the questions coming. I'm always monitoring the chat and always happy to answer as many questions. No question is too stupid, all questions are welcome. Last week we looked at advanced computer vision, we looked at image augmentation. So let me jump out of full screen and head over to augmentations. We looked at augmentations library as well. It's an absolutely fantastic framework, please consider checking it out. And not just for application, it's also written by not one of the absolute best in computer vision. I would say these are Kagglers researchers, and really well versed practitioners. So even their code, it's completely open source. I would encourage you to start diving into the source code as well. Again, it's all up to you. I can only give suggestions based on my small perspective to the world. We also looked at Keras API and how it works with the weights and biases API. So how can you track experiments inside of Keras? It is just one line of a callback, so it doesn't take that much effort. Homework from the previous session, I suggested all of these things. I believe everyone is ready to jump onto Kaggle competitions. I've not seen anyone participate in Kaggle competitions from this group yet, so I would really request and urge you to start competing on Kaggle. It is, in my opinion, one of the best ways to learn. And I'd also suggested playing around with augmentation. I believe I didn't see that yet. I believe Yuvraj had written an incredible summary, which I'm yet to read, so I didn't mention that from the previous session. But again, please consider writing a blog post on augmentations in Keras and submitting to Kaggle competitions. I really think it'll bring you a lot of value. So I believe we've summarized the previous session. We're on to the next bit. We're right in the middle of chapter 9, so I'll try to wrap that up first, and from there we'll try to understand how can we apply deep learning to time series. As a spoiler, there's not many secret techniques being shared there. So it actually introduces you to RNN and LSTM, that is the ground reasoning, and also some structure around time series. But don't expect it to cover a lot of secret tips around time series. It's a small chapter, and if you want a better taste of it, Kaggle. That's why I suggested Kaggle. From there, we'll go into deep learning with text, and I believe generative deep learning will be the last chapter. Again, I've tried not to cover too much theory because, first of all, I don't want to directly share the book's content. These are just summaries of the chapters and some additional thoughts. So I believe we might skip chapter 13 or 14, or we might have a very short session. And I want to hold an extra session where we just do a blogathon or a hackathon of some format. As a reminder, here's what image segmentation is. It's using computer vision. And the point to note here is you could use deep learning or not use deep learning to segment different portions of the image. So this is for, let's say, a self-driving car problem where the car is trying to understand what's going on in the world. And to understand that, it needs to be able to understand every single pixel inside of the frame. And as you can see, humans are probably all labeled with blue. There might be some false positives, which I think is fine for this case. Cars are labeled with the color red. So we're trying to understand every single pixel inside of this image. Object detection requires you to create a box around every object. So you want to understand where inside of the image different objects are and label them with a certain accuracy. And we also looked at how CNNs outshine fully connected networks. So you can also improve them further by adding some regularization, adding width, adding depth, training them on a graphic card, and stuff like that. So I believe that is pretty much the theoretical things I wanted to cover. We have some amount of code that we should be covering today, so I'd like to jump into that. Yuvaram says, hello, thanks for joining us, Yuvaram. Hello. And like always, please keep the questions coming. I'll also mention another repository that I might not be able to go through given my ambitious agenda. So let me pop this up in the banner as well. I've created a repository called Groundbreaking Papers. This is an initiative at Weights and Biases where I'll be covering papers that really change or really introduce novel concepts, hopefully, although that time only decides these things. And this repository will be updated at least once a week. So I'm aiming to release a new annotation every week along with the paper summary and a collab. So if you're interested in being on top of research, I believe this could really bring you all a lot of value. And I'll be using the connet annotation from here to make my life easy. So I've all sorry, this should be con next, but the paper is titled a connet for 2020. So I've already annotated the paper, and if anyone is interested, I would request you to check this repository out. So let's start with chapter 9, part 1, which is where I had left things off. Let me drop the link as well in the chat. Oh, I apologize. Were my slides not visible earlier? I'm sorry about that. Sometimes there's this weird issue with presenting. I'll make sure that doesn't happen in the future. Could someone please also confirm if I should zoom in further or if this text size is good enough? It's this there's a 30-second delay that happens, so I'm quickly waiting for someone to confirm, and then I'll continue. Awesome. Two people have confirmed. Thank you so much. And sorry for the awkward pause there. Um, so the chapter 9 is called Advanced Computer Vision, and there are a few things, different things that are covered inside of the chapter. The first one covers an image segmentation example. So we're downloading from something that looks like a pets dataset. Let's go over there and see if we can find anything on this website. I'm just going to the website from where this was downloaded. And looks like I might have to jump around a few links a bit. So let's see, where was this? Let's try to go to the link directly and see if that helps. Yep, there we go. So we're using the Oxford triple IT pet dataset. This apparently has 37 categories of pets and roughly 200 images for each class. So it's cats and dogs of different breeds. It looks like I didn't know there's a cat breed called Bombay. That's interesting. Um, let's see which other ones do I really recognize. I recognize Shiba Inu for not good reasons, not financial advice, by the way. Um, this is why the internet loves pet images, because you always get lost. Let's come back to business. So looks like we're downloading a dataset consisting of pet images, and we'll be trying to segment these out. And we also have annotations, which of course would be required to segment these out from the background. So inside of this collab, and again, this collab is just from the GitHub repository of the book. I have not written this. It's by Francois himself. So we set the input directly to images. We set the mappings, and we try to sort the input images path like so. And we check for images that end with JPG. This used to be one of the mistakes that I would make, where I would concatenate files which didn't have this file extension, and that would cause me all sorts of problem, because if you're working on a hard disk between different OSs, Mac OS tends to create a garbage uh, file, I believe, and that can cause problems. So small thing to remember, please try to check for this. And the reason why I'm suggesting this is, ideally, the best way to learn, in my opinion, is once you go through this collab, don't just run it like I'm doing right now. I'm doing the worst thing possible for learning. Try to jot down the points of what's going on inside of the collab. Try to understand different functions, which I try to explain in this session, and then try to replicate it by yourself. So I would encourage everyone to follow that approach. So from there, we'll import matplotlib, and we'll import from Keras util load image and image to array. Let's see what's inside of Keras utils. So let's hop over to keras.io, and we'll go to documentation. Let's see utils, enter utilities. There are a bunch of these. I'm trying to find the image data format. Is that the one? I don't think so. It's load image. It doesn't pop up immediately. I believe it might also be plot model, but that I don't want to mix things up. So this might be the one that I'm trying to look for. I believe yes, it is. So all of these help us manage different functions required around loading images. Again, I actually looked this up earlier this evening, and now I'm getting confused myself. But I wanted to show what exactly do these utilities do. So I have another trick to actually try that. Here, I'll put a question mark and see if this helps me. That is taking too long. Apologies for that. Sorry, I just wanted to remind everyone as a quick nudge that you should be checking functions inside of the documentation, or you can use a question mark to check what parameters go into it. So that's what I was trying to do here, but I'll continue without spending more time there. Awesome. So we've loaded the image and we've converted it to an array using different utilities. I'm sorry, I'm trying to keep an eye out on the chat. That's why I keep getting distracted a bit. Uh, we need the image to be converted to an array that from which we can further load it into memory. So that's why we need to do these steps. And also the load image function. Now it tells me what it is. So it loads an image into PIL format. I'm assuming everyone can see this pop up. And if I didn't know this, if you hover over functions in Colab, it shows you the function parameters. I'm not the biggest Colab fan, honestly. So now we can plot this image because I am show expects a PIL image and it can handle that really well. And as you see, it's a cat image inside of the frame. And we can also print, I believe, the mask. So we normalize it first of all because these might not be in the right format. And from there, we print out the normalized array of the mask. So this tells us where is exactly the cat. And this is a segmentation problem. To be specific, it's an object extraction problem, I believe. Kaggle had this competition called Caravana. It happened, I believe, 5 years ago. This is the correct one. So here's another example where such problem could be useful. This Kaggle competition was hosted 4 years ago, and it was quite challenging for the time then. It still is, but now it's at the point where you can, after today's session, apply your knowledge to this. So in this image, you were required to segment out the car from the image and then be able to extract it. So I assume this is for Caravana, the company who is hosting this competition, to be able to produce really nice arts where they, throw in a nice background after extracting the car. Now it's fairly solved, I would say, because Zoom does a really nice job of blurring your background. That is another place where you see this in action. So that's what we're aiming for here. Uh, from there, we try to define different functions around part two, input images, and part two target. So we load all of these. These are helper functions. And now we'll define a simple Keras model. So this is for the first time, I believe, when we see conv 2D transpose. So let's see what that is. Transposed convolution layer, sometimes called deconvolution. The need for transposed convolution generally arises from desire to use a transformation going to the opposite direction of the convolution. So again, we're trying to segment out the cat, and for that we need to be able to run something known as a deconvolution. So we're trying to run an image segmentation, and inside of that we define the architecture like so, where we have a bunch of conv 2D layers followed by conv 2D transpose, and then the output becomes a conv 2D followed by a softmax. So this would be the final model there, and further we compile this model and call it on the dataset. We train it for a while. I crashed my browser earlier, so it's retraining quite slowly. But if you were to train this further, you would be able to predict mass, and I believe it would this time work on a dog image. So to go into more depth, I don't think they tell about this in the book, but this is one of the common ways of, I believe, creating a unit. Unit is slightly different, I believe, to this, but this is one of the approaches around that, and this is how you segment out an object from its background. If you want to learn more about unit, we covered this in a paper reading group on our uh, monthly PRG live stream, so you can check that out, I believe. But this was it for the image segmentation demo, and from there we can jump to modern ConvNet architecture patterns. Let me see if there are any questions real quick. I see a question. If we flip X, Y in the segmentation dataset, will the network generate image from annotation? No, that's not possible because annotation only tells you different. So let's try to understand your question. You are asking if you just have a bounding label around me in an image. You're suggesting if we uh, set the input to just the frame, will it be able to fill in the content? That's not possible because we're not using any technique that can fill in these pixels. These are known as image in painting. So if you're curious, I would request you to look this up. NVIDIA Research has a bunch of repositories and also online uh, demos around stuff like this. Uh, I still don't understand your question. From the mask, I want to generate the image. If for that, I believe you will have to use image in painting, unless I'm confusing your question. Awesome. I'll continue, but please feel free to follow up if that doesn't answer it. So next up is modern ConvNet architecture patterns. Let me ask to anyone in the audience, does anyone want to answer what is batch norm? Or has anyone read the batch norm paper? Why do we use batch norm at all? Why is it useful? So the question is, what is batch norm? I wanted to again, I've been saying this constantly, and at least for the remaining session, I'll keep saying this. But I just wanted to ask if anyone has read the batch norm paper. And I managed to pull it up real quickly on archive. But this had a lot of mathematical equations. I don't want anyone to be able to read this so fast. I'm just scrolling through real quick just to tell what was covered in the paper. So a lot of quite scary equations, honestly, to me. I can't understand what these partial differentiation totally means and what is going on here. Uh, this was a very thorough and very scary paper the first time I looked at it. But let's see, how do we utilize that in Keras? So the question was, what is batch norm? And if you were to, now you might have blog posts around it, but at least when I first heard of it, the best thing was to find the paper and then try to understand it. So I see a bunch of answers already. Let's take a look at them. It normalizes the input to the layer. It helps in training speed. Sometimes works as a regression. Thanks, Anush. That's a great answer. It is used to stabilize the training. That is a great answer as well. I don't know why you all are attending this session. You already know a lot of this stuff, the one that we're going through, the bunch that we're going through. So it's really incredible to see so many answers. Yuvraj says to normalize the data so that values are between 0 and 1. I would say the not exactly the data, but the data being transmitted between the layers. It's a technical jargon between the layers. It's not exactly data that's being transferred. It's how would you classify the knowledge being transferred between layers? I'll have to check what's it exactly called. Again, it might just be data. Uh, Abdul says it's a uh, way to move the mean and standard deviation to 0 and 1. That is a fair answer as well. So the reason why I wanted to cover this was show it to you in Keras code. And let's see it. It says it's a layer that normalizes its inputs. So batch normalization applies a transformation that maintains the mean output close to 0 and the output standard deviation close to 1. Importantly, it works differently during training and during inferencing. To use it in Keras, you just call a Keras layer. Now, the reason why I wanted to go on this investigative round was, first of all, I wanted to show you this paper that is quite scary and does a lot of things. But even inside of the book, when we implement it in simple NumPy code, and inside the book, I believe Francois shares how to implement it in pseudocode as well. It is just a few lines, just a few lines. That is what matters, right? Inside of the code. And he has this very, I want to say, strong opinion. So he says in the book, it's like papers are many times written like how salesmen put on an expensive suit. They're more suited towards making the research look it's like it's very novel or it's very important. So remember, as practitioners, we're coming to this study group. Hopefully, all of you are coming to this study group for, first of all, reasons that I don't understand, since half of you already know this stuff. But we're coming to this study group to be able to apply this knowledge, which is what a practitioner does. Focus on what it does rather than the theoretical knowledge. Many times, papers focus on the theoretical bits. So, machine learning engineer or scientist is a strong job because it requires you to be able to cut through this knowledge with efficiency. So please be efficient with that. Now, this collab is not required. Let me close that. But this collab or this portion of the chapter talks about modern ConvNet architectures. So inside of the paper, I believe Francois uses a VGG architecture to tell you, first of all, that hey, you use modules, and you should be using modularity inside of your code to cover different concepts. That is really important. That is one of the key factor. But there we also cover what are residual connections. These were introduced in ResNets. Now again, don't go and read the ResNet paper. Instead, see what do they do, which is what we're going to do in a minute. And I believe after that we look at what is batch normalization. What is it exactly and what does it do? We've already looked at that, but I'm following the book's order. And then we also get an introduction to depthwise separable convolutions, which were the founding bricks of something known as exception uh, model. I've actually read this a while ago, which is why I see it in my history. Thankfully, nothing else showed up when I typed that. Um, But again, we look at what are depth-wise separable convolution. The key thing that these two is they separate out or they cut down the number of parameters required inside of a convolution model. So the input gets split across different convolutions and then they get concatenated. This is a simplified representation of it. Key thing, as mentioned in the book, is these should be speeding up your computation. But I haven't benchmarked, but to the best of my knowledge and to the book, according to the book, it's a minor speed up. Because what happens in the background whenever you're trying to run any code or any code on your GPU is it or Keras talks to CUDA, which then talks to your graphic card or hardware. So CUDA, since this was one of architecture, or since this isn't so widely used, although it's a very well recognized paper, at least in the book it says that CUDA didn't really hyper optimize this. So even though it's lesser parameters and it makes life easy to train models, the speed up isn't that huge like it should be for that reason. Convolutions are much more optimized. Um, so let's start by going through different things inside of the book in sequence. So dual networks. Let's see if I can find an image. I didn't want to take images from the book, and I've been avoiding that in this session because the book isn't freely available, and I would hate to directly copy material from the book. So instead, this is reliable. So this is from Papers from Code. Papers with Code also has this nice section now where you can just look up concepts. So if you go to a paper that has residual connections, you can simply start going through all papers that have that. So please uh, go to papers with code to find such stuff. But one of the problem inside of convolution networks is, first of all, the gradient tends to become zero. So if you keep multiplying anything by something that's smaller than one, and you can derive this in math, but it'll start to become smaller and smaller in size. So in the paper resonates, or in the paper that introduced resonates, they introduced the concept of residual connection or a skip connection, which does this, where the authors said, hey, why don't we take whatever was going into this layer and add it to the layers after it. So we do this short circuiting of formats where the input here becomes f of x, where f is, literally think of these as the Python functions that are being called for these layers, plus just x, and then it gets propagated. So the Python code for it would be pretty similar as well, but there might be a few things that you need to consider. So since this is all matrix math, you would have to also account for size changes or tensor size changes. So if anything funky is going on inside of here, you would have to pad this input. And padding is just adding either zeros around it to match the size, or you could also add different techniques. So there are different ways of padding this, which I won't go into, but you can look these up if you want. Actually, let's look at Con2D and see what are the padding methods. I'm hoping it's at least a bit elaborate here. If it's not, I'll skip. Um, so we're looking for what is padding. So padding either take one of valid or same case insensitive. I didn't know that. Valid means no padding, and same results in padding with zeros, left or right. So when you're watching any video on YouTube and it has those black bars, that is padded by zero. That's one way to remember it. Now let's hop over to the code and see how REST block are implemented where filters change. So our input is simply a Keras input with the following shape, and the first layer would become a Con2D layer, and we take the residual connection to be just this for now. Then we add another layer that takes in X, and the residual layer now becomes the following. So we pass in the older residual layer, which was just X. This is some smart code, so it took me a bit of writing on paper to understand. But you can simply, you could just write this as X for now. That would do it. But we're passing in the older value, and the newer value now becomes a Con2D of the same. So let's find that image. Where was it? This would be a Con2D. So after both of these come out, these would probably go into a layer which would perform a convolution. So that's what is happening here. And finally, we just add these layers like so. They also cover in the book where if a layer would have max pooling. So in that case, we would have to change the padding a bit. It's quite straightforward, so I'll jump further. Um, you could also define the residual block like so. So first of all, we capture the input in residual variable. From there, x becomes the first input, and then you pass in another it through another Con2D. If there is pooling, and if you would have looked at this block, you would understand how it changes a bit if you're using max pooling. We add a max pooling layer and we apply the condition for residual where we'll add a stride and add filters like so. use a conv of 1 by 1. Otherwise, we follow the older approach. And then we can create as many residual blocks like we want. And this becomes our model architecture. I'll take a pause to see if there are any questions. The text in the book was really thorough around this, so I'm quickly glancing over different topics. Okay, I don't see any questions, so I'll continue. I see one question by Naresh. Sorry, I almost missed that. In what situations batch normalization can be used? We'll just take a look at that in 1 second. So thanks for the great question. There we go. Naresh, you asked it a little too early, but it was a great question nevertheless. Uh, we looked at batch normalization inside of the book, and I believe there was some pseudocode around it. So we put all of these together in a mini exception like model. It's not the exact replica. And like I mentioned, I crashed my Google Colab earlier by crashing Safari. So it's asking me to upload everything. I won't do that. I'll quickly summarize different things though. So first of all, we set the data augmentations to random flip, random rotation, and random zoom. We took a thorough look at this, but we'll flip horizontally. We'll do a random rotation of up to 10, uh, I believe, degrees. Let's take a look at what is 0.1 here. I want to confirm if this is 10% or 10 degrees. Let's see what does random rotation layer say. A pre-processing layer which randomly rotates images during training. Um, if we passed in just one value, that would be factor. And what does factor determine? Float represented as a fraction of 2 pi of tuple size 2 representing lower and upper bound. Awesome. So it's not a percentage, it is a fraction of 2 pi. So that would mean it's being rotated by 0.2 pi. 360 degrees is 2 pi. So 0.2 pi would be up to 72 degrees, if I'm getting that right. If I'm wrong, please feel free to correct me, but I think we'll randomly rotate up to 72 degrees. And then we have random zoom of 0.2. So let's also check what does this 0.2 denote here. Let's look at random zoom layer. So we would be passing in the height factor. A float represented as a fraction of value or a tuple of size 2. When represented as a single float, this value is used to for both upper and lower bound. So I believe this means that we'll be zooming in for plus or minus X%, where X was the input. So we'll be zooming in or out by 20%. How do we decide what augmentations to apply? Great question, Harpreet. We looked at this in the previous session. And the answer is depends on the input. So this one is cats versus dogs. Would you want to flip the image vertically? No, right? No one takes an image of an inverted dog. Would you want to flip it horizontally? I was considering rotating on this live stream. I won't do that, but you could possibly flip it horizontally, right? That makes sense. You could rotate it by a few degrees. That is fine. So for cats and dogs, you can imagine that all of these things apply. You could zoom in and crop into a particular area of the image, or you could pad it with options. So again, it comes through experience. And for weird images, weird being images of stars, galaxies, stuff like that, you'll have to experiment and see. There might be literature around it, but a lot of this comes through practice. Franco actually made this point for a different topic in the book, where he said that a lot of the things in deep learning are just being done because they have been done like so. So please consider experimenting, and if nothing comes out of it, at least you learn something that, okay, this particular experiment didn't work for something. How do we decide point 1 versus point 2? Great question. Again, experiments. You probably wouldn't want to zoom in by 90%, right? So let's take my image right now, for example. I'm in the center of the frame for the most part. You would be doing some EDA on this data set. For some reason, you want to waste your time and find me in an image. That's the task that you've picked up. If you crop into an image, you would be zooming into the middle frame of it. So if I were to do it right now, this is what cropping in does. This would be 50%. This would be 300%, right? So, sorry. Uh, as you start zooming in, you would have to tune the hyperparameter and decide for yourself depending on what images are in the dataset. Aritra answered the question perfectly. So it's a hyperparameter which needs to be tuned, and you could experiment or also strategically, like I said, by looking at different images, decide how to approach that. Thanks, Aritra, for the great answer. Let's see, what do I want to highlight in this part? We make a subset, and this is another technique I want to point out. When you're working with um, a bigger data set, Jeremy Howard actually taught us this in FastJ, and he is one of my favorite teachers. He has really changed many lives, and my life especially. But he taught me this technique, which is also covered here. Whenever you're working actively with or interactively with a data set, make a subset of it that allows you to iterate in 30-ish seconds or lesser. So that's what we're doing here. We're making a subset, and we're pulling out the train data set, the validation data set, and test data set here. We set the data augmentations like so. We've already looked at what all of these do. We will be rescaling the images so to normalize them, and from there we can pass them inside of a contour layer. Now we'll be adding a residual network. Sorry, a residual layer. It's not a residual network. A residual network is a ResNet. My apologies. We are adding a residual layer. So we are doing this short circuiting where we'll add an X to the output. So that's the technique that we're following here, and we call layers.add to add the residual layer. The other thing that we do now is add batch normalization. So batch normalization is a layer that normalizes its inputs and applies a transformation that maintains the output close to 0 and 1. That's what it does. That's all you need to know, and applying this changes things inside of the inputs and makes your model converge a little bit faster. Another thing to note that was pointed out inside of the book is when you are training using batch norm, you need to set it to trainable. And when you're predicting, you need to freeze the layer, which means you don't want it to do funky things where it's changing the or it's trying to normalize because it's already learned and now you're trying to predict. So inside of the layer, it tries to understand how can it normalize what's going into it. When you're predicting, you don't want the layer to learn. Always freeze the layer, otherwise you could run into interesting issues where you perfectly designed a model but it doesn't work. So please be careful around that. And there you go. That's the final exception mini custom model. Any questions from this part before I close this tab? Awesome. I don't see any questions, so I'll continue. Ask them still, and I'll still take them up. So if a layer has, I'll saw a question, so I'll try to answer that. So if a layer has 10 inputs, it will normalize all of them. It's usually a tensor, right? So when you say 10, it could be a tensor of I don't know, some certain dimension. And usually it's like hundreds of inputs. I'll continue still, and as questions come in, I'll answer them. Awesome. I'll close this tab. And now we're at the part where we want to see or interpret what ConvNext learned. So this is known as GradCam. I have crashed this collab, so let's see if I can find something else that I can use. This is a blog post by Ayush Thakur on how you can actually use weights and biases and cam and GradCam. So let me post the link to this inside of the chart. Everyone can follow along. And let's continue here. So this actually tells you about what exactly it does. I'll skip that because I think the visualization is good enough. So when you're training models, it's important to understand what is your model learning. And there are different ways to doing that. So you could look at inside of the layers and what's happening there. Inside of this particular section of the chapter, we visualize the intermediate activations. So we see the activations between layers and try to understand what's going on there. We've looked at this paper earlier in the series where we would understand how does that happen. That is literally what we're doing. That is one of the ways of understanding what's going on. But the more practical way is trying to create a heat map which tells you on images what parts of the image triggered. I want to say the machine learning model because it also applies to transformer model. So if you're using a transformer model or a CNN, what part of the image was helpful in telling the model that, hey, this was a cat or a dog? So this is what class activation maps look like, and this is how you visualize them. This blog is a very thorough walkthrough of the steps required to do that. But I just want to focus on the GradCam output. So that's what I'm scrolling down towards. And this blog would also point you to the original paper that mentioned this. So what does this lead to is an output like so, where since this is a weights and biases report, I can also look at how did the model training change with time. So weights and biases allows you to, this is why I am a fan of reports, especially of Ayush. He writes very neat reports and I would encourage you to read more of his work. But we can look at different steps inside of the model and see how the model has improved. So again, it's this visual way, like I said, of understanding what was happening inside of the model. So now we're predicting, hopefully, I've not looked at the outputs, but hopefully we're telling that this image is a dog and this is a cat. And now we can understand which parts of the image triggered the machine learning model. Why is this important? Let's say I had the privilege to interview Chris Diot yesterday, and he gave this example. So I'm using his example. If you had an image where dogs were just sitting on cars and cats were sitting on boats, your model could be potentially learning how to differentiate cars and boats and not cats and dogs. So understanding the output is really helpful. More practically, if I go to Kaggle is one of the best way of testing your knowledge and embarrassing yourself. I have done the latter mostly, but Chris Diot won a solo gold medal, which is really hard to do on Kaggle. That's a side tangent. I won't go into that. But he was training transformer models. Sorry, I wasn't sharing my screen, so let me do that. Uh, I wanted to point out Pet Finder competition and this leaderboard. And Chris Stewart, absolute legend. He's uh, one of the most respected Kagglers, finished sixth on the leaderboard. And he was trying to train a few transformer models, as he mentioned in yesterday's interview. And to understand why aren't these being trained effectively, he actually visualized the GradCam, which led him to understanding few things. So as I find his solution and share my screen this time, hopefully, there was a trick to making transformer models work. I understand we haven't talked about them yet in this course. So if you are new to transformer models, please don't worry. It's a set of models that's really sexy in research and they work really well. That's all you need to know, that they work really well. It's a hot topic in research because they are quite effective. To make them work, many people were resizing their images like so, which wasn't helpful. So if you correctly crop like so, the transformer models were working more effectively. Uh, as I understood, Chris got this knowledge by visualizing the grad camps. So this is why visualizing all of these layers is helpful. I would again really encourage you to check out this incredible blog post by my colleague Ayush. He writes really well blog posts and is a Kaggle master. I think he'll soon be a Kaggle grandmaster. It's just a matter of time. But please do check out his work. I would really encourage you to spend some time reading these posts. So let's come back to this notebook. I believe this was the gist of the notebook more in a overview fashion. So I'll close this notebook as well and come back and see if there are any questions. Harpreet has shared an example where a model was classifying tree branches as birds. Yeah, that's a problem that happens with a lot of the ML models. That's what we're trying to look out for. Thanks for sharing that, Harpreet. There was a question earlier that I missed. How is batch norm different from layer norm? I believe we'll cover this when we get to NLP, so I'll answer the question then. Thanks for the great question, though. If you're curious to check this out, I will point you to this example blog post. I was actually just reading this a few days ago. This is by, again, one of my colleagues. He's as equally as talented as Ayush, but let me put this in the chat and suggest you to read this as a homework. Thanks for the great question, though. We'll definitely revisit this. So now we're at the point where we're ready to learn deep learning for time series. But before that, I want to come back to my original promise of covering ConvNext. So let me first of all open this paper, and if GitHub render works for a 15 meg PDF, I would be surprised. Oh wow, I'm genuinely surprised it did work. So let me post this link in the chat again. And highlight it like so. So I've annotated the paper that discusses ConvNext architecture, and I'll very quickly give us gist of the paper. And then we'll see we're already at the point where we can implement cutting edge research. This paper came out on 10th of January, barely 15 days ago, just a little over 15 days ago. And this paper asks the main question. Pardon my handwriting. I know it's awful. You don't need to write a chat comment for that. I know that already. But the main question addressed is how do the design decisions in transformers? I mentioned transformers is a really up and coming area of research. Can we possibly take the tricks inside of transformer and apply them to convolutional neural networks? So they modernize a ResNet 50, which means they take different techniques from a transformer and add changes to a CNN. Now, I won't cover the entire paper. That is planned for a paper reading group, and you can sign up for that if you're interested. I'll scroll down and show you the main gist of a ConvNext block. So these would be repeated, I believe, 96 times. And inside of a ConvNext block, here is a ResNet block next to it. Here is a SWIN transformer block. Inside of it, you have convolutions of 7 by 7 being applied, followed by a layer norm. So, Harpreet, pardon me, I know we'll cover layer norm later, but for now, for my argument, believe that it's a way of normalizing. It works. So, we pass it through that. And then we apply JLU, which is an activation function. This is the gist of a ConvNext block. Now let's see what does it look like in code. This was a collab by my colleague Shomik. Shomik is really talented. He's been contributing to Keras.io examples, and please check out his work. He's a Keras ninja. I've come from a PyTorch world, so I'm good at that, and I'm terrified of Keras. So we're stealing his work for our sake. For the sake of research, we're stealing his work, and inside of this, he's defined different blocks, which are conv block, depthwise conv block, and ConvNext block. So what does a ConvNext block use? It has a depth-wise conv block of, remember, kernel size 7 by 7. So let me bring this tab closer. So 7 by 7 conv block, right? From there, ln, layer norm, right? Followed by gelu, and there's a skip connection happening as well there. So we call a layer norm layer and pass it further to a dense layer called gelu, followed by a dense layer. Then we apply a dropout. Dropout, easiest way to remember is making your model drunk. So it forgets different things at a random probability. There's some implementation detail here, but a thing to understand is we call dropout. And then we do the residual network trick, which is where we add these layers. So of course, there's some trick around defining these blocks. So conv block needs to be defined in a particular fashion. And depthwise conv block also is a separate function. Very simply put, I wanted to point out that based on all of this knowledge that we've acquired in just 2 weeks, we are able to understand an implementation of one of the hottest papers in computer vision. So this paper came out 15 days ago and it was really being shared a lot on Twitter. I would again encourage everyone to sign up on Twitter and follow people like Jan LeCun, authors of this paper, who've done incredible work. Really interesting work, I would say. This paper was really shared a lot. And just using knowledge acquired in 2 weeks, we can understand this to some level, right? Again, if you go to the repository that I was mentioning earlier, you can find how to use this in PyTorch, and we'll shortly add the Keras implementation as well, so you can find the code walkthrough as well. But again, wanted to showcase that we're already at the point where we have this practical knowledge. I see a question by Harpreet. What is depth-wise conv block? This is more for the paper reading group, so I believe I'll cover it then. Sorry for not answering it right now. I can answer it later after the live stream as well, just to be respectful of everyone's time. So awesome. We've wrapped up chapter 9 officially, and we're ready to jump into time series. This is meant as more of a introduction to RNNs, and also a broad level overview of time series forecasting. So the problem inside of this chapter is a temperature forecasting example. I want to ask everyone, how would you set up validation and testing for this? So let's say you're trying to predict tomorrow's temperature. Your goal is to predict tomorrow's temperature. How would you set up the validation and test dataset? This is one of the most important parts of working with time series datasets. So how do you split the validation and test it? I'll wait for a few seconds because there's a delay between me saying this, you hearing it, and typing in the answer. Harpreet, our awesome, our most active, awesome member says future time periods are not to be used in training. How would you define future? That's that's the question. Yuvraj, one of our oldest members, says take the latest set of data as validation. Won't shuffle the data during training. That's a perfect answer. Let's see. Uh, what are the other questions? Abdul, I see your question. I'll answer it afterwards, not to break the flow. Ali has a similar answer. Sequentially, first 11 months as train and rest as test. Awesome answers, everyone. Let's see if I can bring up just calendar. I'm trying to make sure if there's nothing on my calendar before sharing my screen. So uh, that might be confidential. Nope, it's all clear. I don't have anything interesting, so I can share my calendar. If you are trying to predict what happens in the next 2 days, well, next 2 days given the previous input, first of all, in deep learning, we tend to shuffle around our data, right? That is actually bad because we're using a trend that would have happened in these previous days leading up to a weekend. Let's say you're trying to predict weekend sales and you use the previous week as input. You first of all wouldn't shuffle this input because that would mess up the trends for the model to learn. The other thing would be your validation test or validation or test set would be the weekend, would be the future weekend, not something from the past. Because you are trying to predict the future using the present. The future is the test set. It's also a test in real life, but it's also the test set here. So the validation and test set would be the future. Sorry, validation and test set would be from the future and not the present. That's what I was trying to say. So that is the key trick to remember. Vignesh is asking window size. We'll look at what that is. I assume not everyone is familiar with that concept yet because that was introduced for the first time in this chapter. So that is one of the key things that we learn in this chapter. The other one is to always start with the stupid baseline. What is a stupid baseline? If I want to predict next weekend sale, I can just take the previous 3 weekends and average them. Or last year's weekend sale for the same week can be this week's sale. Maybe 10% more, assuming we've grown since. So always start with the simple, stupid model because from there you can only and you should only improve. If you are applying machine learning, which is this shiny tool, it should improve on that. So these are the two things that we need to remember. And we download this data set, which has temperature readings spread across different timings. And here is the plot for the same. So we have a lot of readings over many different days. I think it's over a period of inside the data 10 years, I believe. And now we'll just plot the first 10 days. So looks like it's really cold here. This is what minus 25 degrees. That is freezing. I'll need a lot of chai in this temperature. But we set up the text test and train split like so. So we would have probably the training set before this 800 sample. Let's say 800 to 1200 would be the validation set. And the one after that would be the test set. And we would need to normalize the data. First of all, it's always important. Now, when we're loading the data set, we'll use time series data set from array utility. So let's take a look at what that is. And let's also close tabs for the sake of my sanity. We found that. I'll close the other tabs real quick. Time series data preprocessing. This function takes in a sequence of data points gathered at equal intervals along with time series parameters, such as length of sequences or windows. spacing between two sequences to produce batches of time series. So if we want to batch our inputs, we call this function and it takes care of a lot of things specific to time series. That's what I understood from this. And then we can iterate over different weeks like so. From there, we define our training, validation, and test set. Not going into any details. It's literally just splitting this into different windows. Probably just vaguely, maybe like up until 100, 800, we have the training data set. 800 to 1200 would be validation. From there, it'd be the test set, something like that. I might be wrong about the exact numbers. And we batch these. So we'll first of all start with the stupid model, like I said, and from there we'll just do NAE. So someone mentioned, what about a 20-day EMA? I think this would be similar to that. So we just iterate over all of the samples and we just take the sum of absolute differences and we divide the total error by the number of samples. So we take the MAE as a common baseline. From there, we have a model and we can see how accurate it is based on the loss or metrics that we're trying to optimize for. Now we can use machine learning. So now we can pull out our shiny tool and apply it. So what do? We also start with a silly baseline. Silly would be a dense model. So fully connected MLP. We want to learn about RNNs, but we are setting up that. I see a question by Harpreet that I'll come back to in 1 minute. And we would be checkpointing the data, checkpointing the model by calling the model checkpoint callback. Again, I believe, I'm not sure if this is very intentional or I would assume it is, but these different concepts are quite well introduced across different chapters. So we learn of this callback, I believe, for the first time in this chapter. I might be wrong about that. And we create a simple model that just has an input layer, a flattened layer, and a dense layer. And from there, we get the output. That's it. That's all this does. This model would suck. This would be really bad. So we predict the training and validation errors, and as you can see, it's not trained at all. It's actually overfitting quite a bit to the training data set. We can just say that it's not effective at all. It's actually performing, I believe, worse than the stupid baseline. So this was 2.62, this is 2.67. Our machine learning shiny tool has failed us. What a disappointment. I wanted to ask, can you apply convolutions to time series or tabular or NLP data? You can apply it. Would it be effective or not? That is a different question. So the first thing we do here is we apply a conv 1D layer because it's not two-dimensional data. And we call a max pooling layer a conv 1D, another max pooling, another conv 1D. I'm not going into different dimensions because these scale as you increase the depth. So I assume whenever you are implementing these, this is the real job of a MLE to keep an eye out on these parameters. And you only learn this while you're actually implementing this. Spend some time doing that. We call a bunch of conv 1D layers followed by max pooling and then global average pooling layer. And this then becomes our output where we just pass it through a dense layer. Now we can compile and train this model. It is even worse. So convolutions didn't work on time series. Problem. My question is, does anyone want to suggest why convolutions weren't effective for this? So why did the conv 1D model did not work very well for this problem? I'll just wait for 20 seconds before I share the answer. The question is, why did the Con1D model perform worse on this particular problem? Yuvraj says maybe because connects look for local patterns and not global patterns. That's a great answer. That is quite close to the actual answer. So, quite a close call. Himanshu answered it perfectly. Connects do not retain temporal data. Connects split up your images and pass in different many to few mappings, is the technical word for it. We looked at this in the previous section, but we perform convolution dot products over segments. That's not effective for time series because you lose temporal data. So you lose the meaning of time there. If you are to predict graph shapes, convolutions would work well, but that would lose the meaning of temporal data just because how convolutional neural networks work. So it was a great experiment. It confirmed this theory that hey, they don't work well with time series data. So now we are ready to introduce a LSTM based model. And LSTMs are really scary to look at. Let's see what do they look like. I would encourage everyone to check out this incredible blog post by Chris Ola. Let me drop that in the chat. But my point is, these are quite scary the first time you look at them. These were the hottest topic when I first heard of machine learning and NLP, and I spent about 1 month reading this blog multiple times. Simply explained, a recurrent neural network is a for loop in math. I found this through a YouTube video that I can share the link afterwards. I think it was called Transform. Coordinates are dead, long live transformers. That was the original video. I can share the link after this call with the signups, with the people who've signed up. But inside of a recurrent neural network, you have different inputs that are going into the model. And the key thing then becomes the hidden layer for the previous layer becomes an input for the next layer. So it's this looping effect that keeps sending information ahead. This is really effective for different language based problems, but it's also effective for time series because this captures the long term trends inside of time series datasets. So this information keeps getting passed and the model remembers what was happening earlier in this dataset. Uh, RNNs have a problem of vanishing gradients where these numbers start to become zero. So you can't really create deep RNNs, just vanilla RNN. You can't create them. So to tackle that, you create something known as a LSTM, which is this really daunting looking model the first time you look at it. You can read the blog post to understand inside of Keras, it's just a layer. And broadly speaking, it takes care of the fact that you can't create a deep RNN. You can do that here. And it takes care of the vanishing gradient problem. So it trains more effective RNN like model. That's what happens inside of here. We create an input, we pass it through an LSTM, pass it through a dense layer, which becomes the output. Then our model performs better this time. So I think after this, we look at a NumPy implementation of RNN, which I'll skip because it's quite straightforward. And we also look at a recurrent layer in Keras, which was also straightforward. RNNs are a bit prone to overfitting. So we tackle that by adding dropout. So this again is the model same as earlier, And this time we just added dropout layer. So we would have learned in our previous example that the model was overfitting. So this time we added dropout layer, and I was supposed to show you the output, but as you can see, just on 30th epoch, which is halfway through, the accuracy was validation accuracy was a bit better than earlier. So I think we're overfitting again a bit, but the validation accuracy was already better than the previous model. Furthermore, we learn how to stack RNN layers. So there's another model known as a GRU model, which is a gated. Uh, let's look that up so that I don't mess it up. What is a GRU? Gated recurrent unit. I am haunted by this mistake. At one point, I was interviewing for an internship. I'm very happy to be at Weights and Biases, but this was way back when I was interviewing for an internship. I forgot this definition. Let's make me and everyone remember this. The full form is gated recurrent unit. It's a paper from 2014, but that's what GRU stands for. I don't know what what rubbish I came up with, but it wasn't this, and I didn't get that internship. I luckily the same semester went to an IIT where a professor took me for an internship, so things went well. But this is what GRU stand for. Uh, I don't think I'll go into depth of what these are, but again, this is another variant of RNNs, uh, and I think we look at how we can stack these layers effectively. So how can we stack GRU layers and add a dropout after them? Again, this is another model, and we take a look at how this performed. We also take a look at bidirectional RNNs, which should be a bidirectional LSTM. Um, I don't think the book covers a lot of theory around it. It's a simple layer where you simply pass a LSTM layer inside of bidirectional. So let's take a look at what is bidirectional real quick. It's a wrapper for RNNs, and it's not very detailed on what it does. So I'll leave it at that. I think that was it. What for chapter 10? So we've gone through chapter 10 as well, and I'll now take a look at questions before moving further on to covering attention. Let me close this tab and all remaining tabs as well. And now let's take a look at question. Oh, there's been an incredible discussion happening that I missed. Will conv 1D work for small independent sequences like reviews? I don't think so. It's really a word. So inside of a conv 1D layer, even individual characters would get mixed up, I would assume. So it's really not an effective technique. Can we add residual connections in RNN to the make them work? I believe something similar happens in transformers. So I didn't comment on that, Harpreet, because I'm not sure if it's already being done and if it's called the same. Uh, I'll check and speak about this in the first few minutes of the next lecture. So thanks for the question. I think it's being done in transformers. I need to check if it's called the same or if it has a different name. Himanshu is asking, sounds like vanishing gradient should be a problem for any network that is deep enough. Um, I think you're right. Yeah, it is a problem, but it's more prone to RNNs because the if you look at I think there's some analysis around it, but the number becomes smaller faster in RNNs compared to CNNs. Don't quote me on that, but that's why. Sorry, I'm mixing these up. I apologize. It is a problem that prones both networks equally, and it prones LSTMs lesser than RNNs. So LSTMs are lesser prone to vanishing gradients than RNNs. Himanshu is right. I think they might be called a carry connection. That's the term I want to double check. I'll still check and confirm this. Luckily, Yuvraj says it is covered, so I trust his answer, and I'll still. Yuvraj, can you confirm if it's still called residual connection? I've been reading a lot of papers, so I might be getting confused in my head. I'll wait for him to confirm that. But in the meantime, can I have your attention, please? When I say these words, I assume not every one of you is paying close attention to the YouTube video, right? You might have something on the side. You might be looking at reels. But when I said those words, did your brain, hopefully your brain redirected your senses towards the live stream or towards the screen. So the attention module asks this question: how do we encapsulate, how do we capture this into a neural network or into a machine learning model? So how do we make a machine learning model pay attention to different parts? That is what attention layers or modules do. But to understand that, I will use Jay Alamar's blog post on visualizing machine translation, which would tell you the theory of what are the pre-attention approaches. So I've dropped that link in the chat and let me highlight that as well. If you simply look up visualizing neural machine translation, Jay Alamar, on Google, it should take you to his blog post. He also has an amazing YouTube channel that I really enjoy watching. So I would really suggest everyone to check out his channel. I'm subscribed from my different account. I think this is my work account, that's why I'm not subscribed. But again, check out his work. It's really incredible, both the blog post and YouTube. So to translate sentences, you have something known as a sequence to sequence model. So it takes these models broadly, take a sequence of inputs and give you a sequence of outputs. This is why I wanted to use Jay's blog, because it makes my life really easy. He has these incredible animations and I absolutely don't have to do anything. I'm the super lazy person, so I'm using his work. In a neural machine translation, this model would probably be a neural network, and it'll take this French sentence, convert it to English. So it takes a sequence in a different language and converts it to another sequence. How does it do that? It encodes the input to a certain state, and then the decoder decodes the state to the target language, broadly speaking. Uh, Context is a vector that tells how much um, each layer of encoder or decoder should pay attention to inside of the model. So it tells you how much of importance is to be given to, let's say, J sui. So J, let's say, is an important word, or étudiant is an important word. I failed French, but I know enough to like be able to nail that sentence. Hopefully, I nailed it. But étudiant would probably get more importance in context. Hope maybe. So that's what this layer would tell the model. Actually, it's visualized later, so my life is easy. So J sui étudiant, and here's a way of. Sorry, this is not the context vector. So this is how we turn it into word embedding. Sorry, I was mixing this. But let's say étudiant would probably be given a higher importance, so this number probably would be higher for the same. Then we convert these into an array. So we turn the input words into vectors before we start processing them for our outputs. You can simply download pre-trained embeddings also to do this. That makes your life easy. Inside of RNNs, once you've pre-processed these, you simply pass the input vector to the hidden state, and from there it gets passed on further. So the hidden state carries further, and you pass in the later halves or later words into the RNN model. So the first time step, the first word goes into the encoder, second words go into the encoder, third word gets into the encoder. All of these produce hidden states. The first hidden state produces the first output, second gives the second word, third gives the third word. So each input gets marked to a hidden state. Once that is done, that goes to the decoder, and every hidden state gives you an output. So this is how RNNs work. And I think I wanted to specifically quickly show how does attention change this. Um, but I'll probably use the architecture to summarize this. I can point you to Yannick Kilcher's incredible video around this. Or I'll actually also publish an annotated paper next week, so that should help you hopefully to understand this. But inside of this architecture, again, I'm trying to theoretically give an overview of how attention works. So I'll quickly use this architecture. These use a masked multi-head attention. And inside of this, there are three main things that happen. And these are three main inputs that go into this. These are Q, K, V, query, key, and value. Let's see if that's mentioned somewhere in the paper. Yes, it is. So inside of this attention layer, you have a query, you have a key, and you have a value. So internally, as the model learns different things, the model sends a query and a key value associated with it. So, hey, can we see how well is Sanyam's explanation? And then the model takes a look and it says it's absolute garbage. So the value comes out negative. This is actually helpful for training sequential to sequential models, sequence to sequence models, because it makes context awareness easy. So as you saw, LSTMs really learn word by word and pass on the hidden state, but here you can individually query different words. So one of the things that RNNs and LSTM struggle with is long-term association, but this makes it easy to check how different words get associated at a broad level. So very simply put, this is attention layer, or this is scale dot product attention. And this multi-head attention layer really revolutionized our field in a way. First of all, NLP and now computer vision. But I quickly wanted to introduce these two concepts. So we've looked at sequence to sequence models and we've looked at attention. In the next lecture, we'll be taking a look at how can we use these to work on text data. So suggested homework, we looked at a lot of things. One of these were looking at a PyTorch paper that is implemented in Keras. And this was done by my really smart colleague, Shaumik. So I would really encourage you to follow his footsteps and try to do that. I haven't seen anyone submit to a Kaggle competition. I would really, really urge you to start doing that. Please consider playing with GradCam and training a time series RNN or LSTM. And you can, of course, log all of these experiments with weights and biases. Write about this, share it, tag weights and biases, tag me. If you're interested, we're still actively sending swags to any participants. And I believe that was it for today's lecture. That's all I wanted to cover. I'll quickly check if there are any questions. Oops, sorry. I just realized the screen wasn't visible while I was presenting 27 27 days of Keras and homework. So I'll that out. Here's the issue that happens when you're sharing your screen. You can see the presentation, but sometimes it doesn't get shared effectively. Sorry about that. I'll quickly point these things out again. Please consider implementing a PyTorch paper to Keras. That'll be easier because you can quickly map the layers. Again, nothing against or nothing for one framework over the other. Both are incredible. We're here to learn about uh, Keras. Earlier, we learned about PyTorch. Again, whatever works better for you, use that. But if you're learning Keras, port a paper from PyTorch to Keras. Please submit to Kaggle, play with GradCam, log your experiments with weights and biases, and consider training a time series model using RNN or LSTM. Share it on Twitter, share it with the world. Use the hashtag 27 days of Keras. Tag weights and biases or tag me. We'd love to share your work further, and we would love to send some swag to the best participants every week. We're still actively doing that. Thanks again. I can take any final question, and let me quickly see if there are any. No, there are not. And I managed to complete in time. So again, thanks everyone for joining. It's really great to learn with all of you every week. We have 2 weeks of 2 or 3 weeks of this series remaining. The last week will be 1 week long blogathon where I'll invite everyone to write one blog post, and we'll select winners and we'll be sending out swag to the top winners. So the requirements would be the blog should be in Keras, and if you want, it should include bits and biases. We might be biased towards that, or that might be a strong requirement. Uh, Although I suspect it can just be using Keras. Again, please start thinking along those lines. Thanks for joining me every week, and I'll see you next week when we learn about attention, NLP models, and also a bit about generative art. Thank you so much, and I'll see you tomorrow.